They've survived for over 130 million years. They've outlasted dinosaurs, ice ages, 5 mass extinctions that wiped out most life on this planet. And right now, there are over 20 quadrillion of them on Earth. 20 quadrillion. That's more than the number of stars visible in the entire observable universe. But every single ant colony, no matter how massive, no matter how ancient, no matter how perfectly organized, carries a hidden flaw. A flaw so precise, so predictable, that once scientists identified it, they learned to exploit it completely. And the strangest part isn't what the flaw is, it's how long it took us to realize we share it. Here's something most people never stop to consider. Ant colonies don't make decisions. Not really. The queen doesn't give orders. There are no generals issuing commands, no lieutenants coordinating strategy, no central nervous system processing information and directing responses. Every single ant in a colony of millions operates on one thing alone: chemical signals. Invisible molecules drifting through air and soil, interpreted in fractions of a second, triggering automatic responses with no deliberation whatsoever. Which sounds like a limitation, until you watch a colony in action and realize that this system, this blind chemical obedience, has produced some of the most sophisticated collective behavior ever observed in nature. Farming, architecture, warfare, medicine, waste management, all of it, no brain required. But here's what that efficiency costs them. And here's where the story gets genuinely unsettling. In 2009, a team of researchers in Belgium set up what looked like a routine behavioral experiment. They synthesized a chemical, a precise molecular replica of the pheromone ants release when the colony is under attack. Not a rough approximation, a near-perfect copy. They introduced it into a healthy, thriving colony of over 200,000 workers. And then they watched. What happened in the next 6 hours would reshape how biologists think about collective intelligence and its limits. But to understand exactly why it unfolded the way it did, you need to understand something about the architecture of an ant colony that most people get completely wrong. Because an ant colony isn't a society, it's a body, a single distributed organism where each ant functions less like an individual and more like a specialized cell. The queen isn't a ruler, she's a reproductive organ, the only one the organism has. The workers aren't employees, they're the circulatory system, transporting nutrients, clearing waste, maintaining constant chemical flow. The soldiers aren't an army, they're an immune response, activated only when the body detects invasion. And like any body, the entire system runs on one thing: chemical communication. Pheromones that say, follow this trail. Pheromones that say, food source located here. Pheromones that say, larvae need feeding. Pheromones that say, intruder detected. Defend now. The colony doesn't deliberate. It doesn't weigh options. It receives a signal and responds. Every time, immediately. For 130 million years, that speed has been the advantage. The problem, the vulnerability, is that the system was never designed to ask where the signal came from. So when the Belgian researchers released their synthetic alarm pheromone into the colony, 200,000 ants had no mechanism to question it. The signal said, "We are under attack," and the colony believed it completely. Workers abandoned every active food trail simultaneously. Soldiers poured toward the colony entrances in numbers far exceeding any real threat the colony had ever faced. Nurse ants began emergency relocation of larvae, moving them deeper, faster, in patterns typically reserved for catastrophic flooding or predator breach. The entire colony shifted into maximum emergency response for a threat that existed only as molecules in the air. And here is where something unexpected happened, something the researchers hadn't predicted. When a colony sustains full alarm state with no actual enemy to engage, the soldiers don't stand down. They can't. The signal is still broadcasting. The chemical message is still real to every ant that receives it. So they keep searching, keep probing, keep trying to locate the source of the danger. And when they can't find it outside the colony, they start looking inside. Minor confrontations began breaking out between nestmates. Workers who had foraged side by side for weeks began behaving as if the other were suspect. Soldiers began performing aggressive inspections on their own colony members, pressing mandibles, releasing alarm signals of their own, amplifying the chemical chaos. The colony, with no enemy to fight, had begun treating itself as the enemy. Within 6 hours, brood care had essentially collapsed. The food supply was halted. Several thousand ants had died in internal conflicts, not from any external threat, but from the colony's own immune response turning inward. The researchers had done nothing except introduce one chemical message, one fake signal, and it nearly destroyed a superorganism that had no other weaknesses. At least, that's what they thought at first. Because, as it turned out, nature had already discovered this vulnerability millions of years before any human researcher did. And what evolved to exploit it is far stranger than a laboratory experiment. Lomechusa stremosa, a small, unremarkable-looking beetle, roughly the size of a large ant, that has spent an estimated 50 million years perfecting a single skill, becoming chemically invisible inside an ant colony. Not physically invisible, chemically invisible. The beetle produces a cocktail of compounds that mimics the colony's own internal scent profile, the specific molecular signature that every ant in a colony carries, that marks them as members, as trusted, as safe. When a Lomechusa beetle approaches a colony entrance, the guards don't sound an alarm. They do something that still strikes researchers as almost impossible to watch without a sense of unease. They pick the beetle up, gently, carefully, and carry it inside, like a returning nestmate, like someone who belongs. Once inside, the beetle begins moving through the colony with complete impunity. It approaches the brood chambers, the most protected area of any colony, where the eggs and larvae are kept. And it begins feeding, slowly, steadily, on eggs, on larvae, on the colony's entire reproductive future. And the ants surrounding it continue to groom it, feed it, treat it with the chemical deference they'd show any trusted colony member. Some researchers describe watching this as one of the more disturbing things in behavioral biology, not because it's violent, but because the colony is actively, tenderly caring for the thing destroying it, and has absolutely no capacity to perceive the contradiction. The chemical signal says, this is family. So it is. But the Lomechusa beetle, for all its sophistication, is still operating at a relatively simple level. It exploits the colony's trust. It feeds. It reproduces. It is, in the end, just an opportunist. What comes next is something else entirely. Something that doesn't just exploit the colony. Something that uses it. Ophiocordyceps unilateralis. If you've never encountered this organism before, take a moment before we continue. Because what it does to ants is so precisely engineered, so surgically specific, that for years after it was discovered, researchers genuinely struggled to accept that it could have evolved through random natural selection. It's a fungus, and when its microscopic spores make contact with a carpenter ant, just landing on the surface of the ant's body, a process begins that will end with near-perfect reliability in the ant's death. But not immediately, and not randomly. The fungus doesn't infect the ant's brain. This is important. This is the part that stops people. It infects the muscles. Specifically, the muscles responsible for the jaw, the legs, the body's postural control. and then it begins producing a suite of compounds. Researchers have identified several, including a modified form of a compound that affects neuromuscular junctions that progressively override the ant's voluntary control of its own body. The ant doesn't know this is happening. To the ant's nervous system, the signals arriving from its muscles feel normal, feel like its own. But the fungus is rewriting them. Over 3 to 7 days, the infected ant begins to behave strangely. It becomes disoriented. It wanders away from established trails. It separates from the colony. And then it climbs. Not randomly, specifically. The infected ant locates a plant, typically a specific species of plant, and begins climbing. It stops at a height that has been measured across thousands of observed cases to cluster with remarkable consistency, between 25 and 30 centimeters above the forest floor. This is the precise altitude where temperature and humidity optimize spore dispersal for this particular fungus in this particular environment. Then the ant moves to the underside of a leaf, finds a leaf vein, and bites down. The jaw locks permanently due to muscle convulsions triggered by the fungus. The ant dies in this position, attached to the leaf. And within days, a stalk begins growing from the back of the ant's head, extending upward, maturing, then releasing spores downward to the forest floor below, where other ants walk. What researchers found when they began analyzing this process in detail was not just remarkable, it was troubling in a very specific way. The fungus isn't improvising. Every element, the height, the plant species, the jaw attachment, the spore release timing, appears calibrated, optimized, shaped by millions of years of coevolution with its host. The fungus has, in a very real sense, learned the ant, learned its chemistry, learned its neuromuscular architecture, learned how to send signals through its body that the ant cannot distinguish from its own. Which brings us back to the core question. If something can do this, can take over an ant's body so completely that it moves, climbs, bites, and dies exactly where and how the fungus needs it to, why can't the colony detect it? Why doesn't the immune response that handles so much else handle this? And the answer, when researchers found it, was one of the more striking discoveries in recent behavioral biology. Because it turns out, the colony can, just not always, and not completely. Worker ants can detect early-stage Ophiocordyceps infection in nestmates before any behavioral symptoms appear. Before the ant starts wandering, before it separates from trails, before anything visible changes. Somehow, through mechanisms researchers are still working to fully characterize, the colony identifies something chemically off about infected individuals. And when it does, it acts immediately. The infected ant is picked up by workers and carried, alive, away from the colony. Far enough that spores cannot easily reach the nest. It's left there, alone, not killed, just removed, isolated from everything it has ever known, at a stage when it probably has no idea anything is wrong with it. Studies have documented this happening within 24 to 48 hours of initial infection, well before the fungus achieves enough control to alter behavior. The colony's detection system is, in other words, faster than the parasite's takeover, which is extraordinary. But it raises the question that makes this story more than just a biology lesson. If the colony can detect Ophiocordyceps, a manipulation that operates at the level of individual muscle fibers, that produces no gross behavioral changes, that leaves no visible mark, why can't it detect the fake alarm pheromone? Why can't it detect the Lomechusa beetle, a creature producing a scent profile that, however sophisticated, is still a copy, still something foreign? Why does the same system that catches microscopic fungal infection completely fail when a beetle walks up to the door wearing the right chemical costume? The answer is uncomfortable, and it's not actually about the parasites at all. It's about what the colony was built to optimize for. Speed. In a system where every decision is made in milliseconds, where the difference between a colony that survives a predator attack and one that doesn't is measured in seconds, there is no room for verification. No room for the neurological equivalent of, wait, let me check that again. The colony evolved to trust signals completely, immediately, and unconditionally, because hesitation, even for a moment, cost lives. The Ophiocordyceps detection works because it operates through a different channel, not the fast alarm signal system, but a slower, more granular chemical profiling system that runs in the background constantly. The alarm pheromone and the Lomachusa mimicry work precisely because they target the fast system, the one with no verification step. The vulnerability isn't in the chemistry. The vulnerability is in the architecture. A system built for speed cannot also be built for skepticism. You have to choose. And for 130 million years, the ants chose speed. And here is where the story stops being about ants, because the human nervous system made the same trade-off, not with pheromones, with something else. We have fast processing systems, systems that respond to social signals, to emotional cues, to environmental patterns, without deliberation, without verification, often without awareness. We have slower, more analytical systems that can, in principle, check the fast system's conclusions. But the fast system responds first, always. And in most situations, by the time the slower system engages, behavior has already been shaped. We've known this for decades. Social psychology has documented it extensively. The degree to which human behavior is driven by signals we don't consciously process, from sources we don't consciously evaluate. The ant that carries the Lomachusa beetle inside isn't stupid. It's doing exactly what its architecture was designed to do. The question that doesn't have a clean answer, for the ant or for us, is whether a system can be redesigned from the inside. Whether something built to trust can learn, structurally, to verify. The Belgian colony recovered when the synthetic pheromone finally dissipated, when the fake signal faded from the air. The alarm response gradually collapsed. Soldiers stood down. Workers returned to food trails. Nurses resumed brood care. Within 48 hours, the colony looked functionally identical to what it had been before the experiment. No visible damage, no modified behavior, no sign that anything unusual had occurred. And here is the part that stayed with the researchers. No adaptation. The colony had undergone 6 hours of self-destructive chaos, triggered by a signal it had no ability to question, and emerged from it with no new mechanism for questioning signals. Ready, completely ready, to be triggered again in exactly the same way. Because the colony can't learn that lesson. Not individually, not collectively. The architecture doesn't allow for it. The same signal, introduced again tomorrow, would produce the same response. Every time. So next time you watch an ant moving along a trail, fast, certain, unwavering, following a path it didn't choose with a confidence it didn't earn, ask yourself what that certainty is actually based on. Because somewhere in the forest, right now, a Lomachusa beetle is walking toward a colony entrance, and the guards are already starting to recognize it as one of their own.